Gonna go ahead and hit the lesson objectives. Welcome to week 2. Before I get started, a little bit of housekeeping. We're going to have an exam later this week. It's going to be online. It will be in multiple choice format, but it will have some questions that will require some problem solving. You'll need to write that out and send that as an attachment. I'll be uploading an announcement later, like maybe tomorrow, that details what the exam will look like. My goal, if I can set it up correctly in Canvas, is to give you the whole day of Friday to do it. But like when you activate it, you'll only have like an hour, right? So you can choose anytime Friday to actually do the assignment, but when you actually open it up, it should only have an hour for you, and you'll have to go through the Respondus lockdown browser stuff. So again, open book, open notes. So you can have that kind of on hand. Okay, and let's get started with the lecture. Okay, lesson objectives. So today we're going to move into kind of like crystallographic points, directions, and planes. So that's going to dominate what we're going to talk about today. So we're going to label point coordinates of multiple positions in a unit cell. We're going to sketch the direction within a unit cell corresponding to 3 direction index integers. We're going to calculate linear density of atoms along indicated direction. Specify the Miller indices for a plane that has been drawn within a unit cell. Calculate planar density of atoms on an indicated plane. Describe how FCC and HCP crystal structures may be generated by the stacking of closed-packed planes of atoms. Differentiate between single crystalline and polycrystalline materials, and define isotropy and anisotropy, and explain how this relates to single crystal and polycrystalline systems. And we're going to explain allotropy and polymorphism. Okay, so we're going to go ahead and start with point coordinates. So last class we talked about crystallographic planes. That's a tongue twister. I'm sorry, we didn't talk about planes, but we talked about unit cells, and we talked about crystal structures. So now we're going to be talking about these crystal structures in terms of how can we identify the positions inside of these crystal structures that the atoms lie in, and communicate the different directions, directionality in crystal unit cells, and talk about crystallographic planes and point coordinates. It'll become more clear as I get into it. And that is a D, in fact. So we're just going to talk about point coordinates. So our people who play Minecraft will, this will probably come pretty easily to you. So we're going to start by drawing a 3-dimensional grid, or a three-dimensional Cartesian coordinate system. So there's those, and we'll have... This will be our x-axis here. Blue will be the z-axis. And let's see, red will be our y-axis. Okay? And then inside of this system, or inside of our Cartesian coordinate system, we're going to have our unit cell. So I'm just going to draw that real quick. Okay, so we've just got a little box, right? Now, I want to be able to identify points inside this system. So let's say I've got a point right here, and I've got a point right here on the very end of the box, and then I've got a point right here. Well, how might we actually think about these points? Well, if we think about a typical Cartesian coordinate system, we would just say, well, this point right here is at x whatever, y 0, right? And then z something, right? But since we're in a pretty well-defined region, we've got one unit cell, we can just say that the distance from the origin to the end of the box is 1. We can just call that 1. So that this point would then become, I'll write it in yellow, x, right? So we could just say 1/2. Y is again 0. And then z is equal to 1, right? And then down here, this point right here, you might be able to guess what that is just by looking at it. And it will indeed be, I could actually probably should not be drawing parentheses. Give me just a second here. Just to make sure. Yes. So I'm going to actually go back on something real quick, and I am going to remove these parentheses. We will not be using parentheses for this. That's important. It'll be clear why that's important later on. But in a typical system, when you're identifying a point, you would use parentheses, right? But not for point coordinates, for a crystal structure, a unit cell of a crystal structure. All right. So we have 1/2, 0, 1. For this one, we're going to have 1, right? X1, Y1, Z1, right? And now for this this point over here, if I just draw a little thing for it, you might be able to guess that X is going to be 0, Y is going to be 1, Z is going to be 1/2, right? And I could do all sorts of things, right? Like I could have a point literally anywhere inside of this frame of reference, and I could point out what those positions are. I've just chosen examples that are on the edges for clarity, but you don't necessarily have to have points that are on the edges. You could have a point on the inside, like right here. Of course, it's super difficult to see, right, from our perspective. You'd have to have 2 different perspectives of this 3D geometry to see where that point is. But I could have one here, and it could be like 0. Well, I shouldn't say 0.3 because we're not using that. We're using fractions. But I could just say 1/3, 1/3, 1/3 for that one, right? So I'm drawing these for simplicity on the edges. They don't have to be. Okay. So I'm just going to say point coordinate. And if I were to define that for you, a point coordinate is just a lattice position. In a unit cell. I think my handwriting is getting slightly better. You might disagree with me. I wrote unit there pretty rough, but I'm doing my best, y'all. And then ABC, so like, you know, ABC would be like your X, Y, and Z coordinates, and these will be in terms of fractions. So I'll just say A over A, B over B, C over C. And these align up. And these align with the X, Y, and Z directions. Right? And again, we're not going to enclose them. We're just going to leave them open, which is weird. It's not what we typically do, but that's how we use this for notating a point coordinate in a unit cell. Okay, so those are pretty simple. Next, we're going to move into crystallographic directions. Okay, so how do we navigate in this system? How do we talk about directions or directionality within a crystallographic unit cell? Okay, and so again, I'm going to draw us our 3D Cartesian coordinate system. And inside of this, we're going to have another box. I'm going to draw it solid this time. Okay. And now I'm going to draw some arrows. So let's do this vector. Let's do this vector. And taken together, they're kind of hard to see. And we're going to do like this vector here. Okay. All right, so these are crystallographic directions. And all I'm doing with this is I'm saying, okay, I have my unit cell, and I want to talk about something in this crystallographic unit cell that tends to be oriented in a certain direction. So if you go back and you look at the diamond unit cell from our last lesson, you'll notice that there are a bunch of different carbon atoms littered around the inside of that system. You can use point coordinates to identify those, but if there's some kind of directional component to that you want to talk about, you can list a crystallographic direction that's associated with that. What we also do with this is we can use it to talk about stacking sequences as well. I think I covered that a little bit in one of our prior lessons. But anything that has a certain direction associated with it, you can talk about using this notation. Okay, so let's talk about some rules. So this one is a little bit more complicated compared to our point coordinates. That was pretty simple, but this one is a little bit more difficult, right? Like, how would I define a vector that starts on this edge and ends on that edge? It's not quite as clear, but I have some rules for you. So to determine your vectors, or what we're going to call direction indices. Direction indices. Okay. Step 1. We're going to get the coordinates of the vector tail and the vector head. Right? We can see the head here and the tails over here. So let's just go ahead and get those for this one. We'll use this one as our example. So the tail for this one, if we just, and again, we're going to use our point coordinate notation for this. So the tail is going to be at, oh, I need to draw my labels, X, Y, and Z. Okay. So the tail is going to be at 1/2, 0, 1. And the head is going to be at 1/2, 1, 1. Hold on, 1, 0. Okay. So we've gotten our coordinates for the tail and head. So I'll just write a little tail and head. Okay. Step 2. We're going to subtract the tail coordinates from the head coordinates. Okay, so if I just draw a little line and we do a subtraction, so we're subtracting the tail from the head. So 1 minus 0 is 1, 0 minus 1 is minus 1, and then 1/2 minus 1/2 is 0. Oh, we can't see that. Okay, so 0. Okay, then I'm going to get this. So we can keep talking about this using the same frame of reference. So all we've done here is we've gotten the, we've subtracted our tail coordinates from our head coordinates. Subtract tail from head. Actually, I'm sorry. So the other way. It'll be 0, 1, minus 1. Which makes sense because we're starting at the head, ending with the tail. And then I'm just going to do there we go. Okay, that makes more sense. All right. And another way to write this is x2 minus x1 divided by a, y2 minus y1 divided by b, and z2 minus z1 divided by c. Okay. Now you might be asking, well, we've done x2 minus x1, y2 minus y1, and z2 minus z1. But what is this divide by a, b, and c stuff? Well, that's step 3. Okay. Step 3 is to normalize in terms of our lattice parameters a, b, and c. Normalize in terms A, B, and C. Now, what does that suggest? Well, it suggests that, you know, given our lattice parameter, like right here, this would be A. This distance here from here to here would be B. And then this distance would be C. Okay? What that suggests is not all unit cells are perfectly cubic, right? They can be squished in like parallelogram, like they can be non-even shapes essentially. They don't have to be cubes. So A, B, and C don't have to be equivalent. That's what I'm trying to say. So step 3 is we have to normalize these values in terms of our lattice parameters A, B, and C, right? Well, what does that mean for our guy over here? Well, for my example case, this is a cube. So A, B, and C are equal to 1. So we divide 0, 1, and negative 1 by 1, and we just get the same thing out. So through step 3, we still have 0, 1, and negative 1. All right. Step 4. Now we reduce to smallest integer values. Okay. Which 0, 1, and negative 1. What's the smallest integer values of those? Well, 0, 1, and negative 1. So we're fine there. And then finally, 5 is we enclose in brackets. Okay. So we're going to go ahead and do that. And I'm going to draw a little arrow. And we're going to enclose these in brackets. There we go. So now why do we do that? Why do we enclose in brackets? Well, so we can tell this apart from a point and also from a plane, which we're going to discuss in a minute. So that 0, 1, and negative 1 is now our value for this crystallographic direction. Okay, so let's try another one. Let's do this long diagonal here. Okay, so we're going to do, I'll just draw, example. Okay, so we're going to do this one here. So let's get our point coordinates for the tail. Well, we'll start with the head actually. So starting with the head, and again now I'm running into that problem, so I'll need to copy it and paste it again. There it is. Okay, so now starting with the tail, or starting with the head. 1, 1, 1. Oh, whoops. Okay. And then we're going to have the tail, which is going to be 0, 0, 1. There we go. Now we're going to subtract the tail from the head. So do this. 1, 1, 0. Next, we're going to normalize in terms of our lattice parameters. Again, for my case, it's going to be 1, 1, 1. So we just divide everything by 1, and we get the same thing out. Next, we're going to reduce to the smallest integer values. Again, this is 1, 1, 0, so it's at our smallest integer values. And now we're going to enclose in brackets. So this would be our answer. Okay, and then let's go ahead and do this one over here. So this one's going to be a little bit more interesting. So we're going to start with 0, 0, 0 as our tail. So I'm just going to put that down here. And then our head is going to be at x0, y1, and z1 half. Okay, so we subtract the tail from the head, and we just get the same thing again. We normalize in terms of lattice parameter values. Again, all equal to 1, so 0, 1, 1 half comes out again. Next, we reduce to the smallest integer values. That's where this gets a little bit more interesting. The smallest integer values here is actually going to be where we actually have to multiply this to get integers. So we're going to multiply this whole thing by a factor of 2. And then that'll give us 0, 2, 1. See how we did that? We noticed that this needs to be an integer, and we just multiplied everything by 2. And this still works. This still works because the ratios are the same. Okay. And then we enclose in brackets to finalize. All right. Next, we're going to talk about crystallographic planes. All right. Okay, these are common crystallographic directions, so we're not quite done with that yet. But these are common crystallographic directions that you'll see: 1, 1, 1, 1, 1, 0, and 1, 0, 0. And again, I could just tell you this, right? Notice how also this is actually kind of offset a little bit, right? Like our Cartesian coordinate system does not necessarily have to be perfectly perpendicular. Okay, just keep that in mind. But also, I could just give you these direction indices, and you should be able to draw the line, right? So like if I've got 1, 1, 1 here, I'm thinking, okay, well, I have to be able to reach the farthest extent of my unit cell in all 3 directions. So I'm probably going to have to start at the very bottom, or at the origin, and work my way out. And that's typically how we do this. We kind of assume that we're starting from the origin until we're proven otherwise. And the way that we do that is, if, for example, we have a crystallographic direction that's negative, for example, so if it's negative, we usually want to think about it in terms of starting from another unit cell and working our way towards the origin. Okay, because you can have, for example, because these crystallographic directions are kind of the same throughout all unit cells, you could be starting over here. Okay, so actually let me draw an example of that to make it more clear. So let's just say there it is. So let's just say I've got a unit cell here. And I'm not going to spend too much time making it look pretty, just for the sake of argument. But let's say I've got another unit cell of the same type over here, okay? Well, this let's just call it this right here. This direction is 1, 1, 1. But this direction is also 1, 1, 1. Okay? They're the same. So if you're drawing your vector and you get something like this, oh, shouldn't be using that color. You get something like this. Well, you can actually just translate it over to your unit cell. Right? Okay. Let's move on. Okay, so yes, these are our common crystallographic directions. And yeah, 1, 1, 1, 1, 1, 0, 1, 0, 0. Okay, I've already talked about those. So next, we're going to talk about linear density of atoms. So let's move back. Okay, linear density of atoms. One of the reasons why we like to talk about line vectors and unit cells is because then we can calculate linear density. So linear density, or I'm just going to call it LD here, is going to be equal to the number of atoms centered on one of your vectors. And that's important. It must be centered on a direction vector divided by the length of the vector. That's what we call linear density. Okay. So let's give an example. I'm going to have a unit cell. Okay. And I'm going to have a we're actually going to draw the atoms in this. So we're going to have, it looks like a FCC cubic unit cell. So we're going to have 4 on the edges. It's face-centered cubic. I'm going to draw the faces in yellow just to make things more clear. I found that that's a lot easier than trying to draw all of your like blue atoms, and that's really confusing. Okay, so here's our FCC crystal structure, and I'm going to draw a vector in red from here to there. Okay, so I'm starting at this position, ending at this position. It's a straight line. Okay, so for FCC, and this is going to be actually aluminum. So just to kind of make it a little bit more real, this is aluminum. And we're drawing this vector. You can kind of think about for a minute what this vector is. And it's actually the 1, 1, 0 vector. Okay. Actually, a quick question. Can I actually draw this twice in the same unit cell? Yeah, I can draw it down here too. And it's the same vector. Which is okay because it doesn't change anything, right? Okay. It's just that technically we're talking about the top of this bottom unit cell, right? But it's the same location. So anyway. Okay, so aluminum in 110. So this FCC crystal structure is going to have 2.5 atoms plus 1. That's how many atoms are actually in the two 1/2 atoms plus 1. And that'll give us 2 atoms. Okay, so how does that work? Well, we have 1 atom here, 1 full radius of an atom, think of it that way. And then we have 2 1/2 atoms on the corners, okay? So if I were to draw this real quick, like from a side angle so we could see it, using our actual atomic density graph, it'll look something like this. Okay, with our red arrow going through it. Kind of like that. There we go. And so we're kind of getting a little bit of how much of the atom in terms of a function of like a one-dimensional function, right, is like actually present in the line. So in this case, we've got 2 1/2 atoms here and here, and 1 full atom in the center, okay? And for aluminum, our value of A is equal to 0.405 nanometer. Okay, that would be this distance here. And so our linear density function, LD, is equal to 2 atoms divided by the root 2 times A. Now, why is it root 2? Well, if this is A, then this line here would be the length of that line. And this will be equal to 3.5 nanometers. Actually, sorry, not nanometers, atoms per nanometer. Atoms per nanometer. So what that tells us is that for every nanometer along this vector, we're going to run into 3.5 atoms. So it's linear density. Okay, so next we're going to talk about crystallographic planes. Okay. Okay, so crystallographic planes. Okay, so I'm going to go ahead and draw another one of our Cartesian coordinate systems. And inside of it, I'm going to draw another box. I'm going to draw a little bit bigger this time. There we go. And inside of this, I'm going to draw a plane. Just like this. Now, actually, let me use yellow. I was going to draw it red, but yellow will work just fine. Okay, so in this, now I'm going to draw just kind of some shading so that we can see what the plane looks like. So now we actually have a two-dimensional plane. This actually extends beyond our unit cell. It extends throughout the entire crystal lattice. But within just this unit cell, we can see like what area it covers inside the unit cell. So that we typically keep it refined to that. So that's what it's like. And given a plane in the unit cell, so we're going to have questions in this class and on your exam that are similar to this. So given a plane in the unit cell, determine what are called the Miller indices. Miller indices. Okay. And so Miller indices, like we've been talking about before with point coordinates and now with our vector indices, these are, when we talk about planar indices or plane indices, we call them Miller indices because the researcher who first came up with them was named Miller, and so now we have Miller indices. Okay, so step one. If the plane passes, so we're going to go through each step that we need to find. We need to go through to find what the indices for this plane are, right? So how do we differentiate this plane from a different kind of plane, right? Like if I had a plane like halfway in here, like through the z-axis, how would we call that plane? So step one. If the plane passes through the origin, so if it passes through the origin, we are going to establish a new origin in a different unit cell. Okay, simple enough. So again, if I come back up here, and let's say I have a plane, and part of that plane touches our origin here. Let's say it looks like, oh man, it's going to be hard to draw it, but let's say this is our origin up here, and I have a plane that's actually perpendicular, or I'm sorry, parallel to our vision, and it kind of, passes out like this. We could establish a new origin right up here, or in a different place, so that the body, a large portion of the body of the plane passes through our unit cell, right? So we can just move over to the left one unit cell or up one unit cell, wherever we need to go to reestablish a new coordinate system. Step two. Next, we're going to read off values of intercepts of the plane. Okay. So these are designated by ABC. That's a B. With your XYZ with your XYZ axes. In terms of your distances A, B, and C. Okay. So let's copy this one down. The third step is to take the reciprocals of those intercepts. Okay. Next, we're going to normalize the reciprocals in the same way that we did before for our vectors. We're going to do that again by multiplying by A, B, and C. Step 5, we're going to reduce the smallest, we're going to reduce to the smallest integer values. And then finally, we're going to enclose in parentheses. Okay. I'll just draw an example. And that's why we don't draw our points with parentheses, because parentheses are reserved for plain Miller indices. And so this, once we complete step 6, we have Miller indices. Okay, so now let's walk through an example. Okay, so here's our plane. And what we're going to do is we're going to actually draw kind of a matrix style system that will help us walk through all of our steps. So if I just draw them right here, we're going to have steps 1 through 6. Okay. And then we're going to have X, Y, and Z over here. Let me draw them a little bit farther out so we have more room. Okay. And so our first step is to relocate the origin if needed. So we ask ourselves a question. So do we relocate the origin? Well, now, recall, when do we relocate the origin? What's the condition that needs to be satisfied for us to need to relocate the origin for this to identify the Miller indices of this plane? Well, if the plane passes through the origin, well, it doesn't pass through the origin, so we're good. So in that case, we're going to go ahead and continue. So the answer here is no. No. Okay. Next, we need to find the intercepts. Okay, so now we're going to take a look at this plane. We're going to say, okay, where are the X, Y, and Z intercepts of this plane in this system? Well, we intercept with the x-axis at 1. So we're going to, well, I could say 1, but really it's A, right? So we're going to say A. We intercept with the y-axis at A. In this case, I'm going to just put B here. So remember, we talked about it in terms of A, B, and C. At B, sorry. And then Z, where do we intercept the Z-axis? Well, this plane is actually parallel to the Z-axis, and it's not touching it. So it will actually never touch the Z-axis. So in this case, what we're going to do is we're just going to say infinity, a little superscript infinity C. Okay? So that's how we determine that. So that's just going to be infinity C, because we never intercept with our Z-axis. Next step, we get the reciprocals. Okay, so A over A, B over B, C over C. It ends up being 1 over A, 1 over B, and for infinity, we get 1 over infinity C. and then we normalize that. I was skipping it. I was kind of skipping a step in a way when I said a over a. But now we actually go into normalizing. So we normalize by multiplying by a, b, and c. So now we have a over a, b over b, and we're going to have c over infinity c. Okay. With the c over infinity c stuff, just bear with me. You'll see how that kind of works out. Step 5. We now reduce the smallest integer values. So reduce to the smallest integer values. Well, a over a is 1. So we're just going to put 1. B over b is 1. And then c over infinity c. So now think about that for a minute. What would infinity, what would a scalar value, even 1 here would make sense too. 1 over infinity or c over infinity, well, that has to be equal to 0. And so that's just what we're going to put. Any scalar real value divided by infinity is going to equal 0. And so that's how we keep it. And now finally we just enclose in parentheses. Oh. And that'll give us 1, 1, 0. And there's our Miller indices for this plane. Okay? So let's try another one. Well, we're going to try a more difficult one. We're going to draw our box. I'm going to go ahead and forego the x, y, and z axes here for brevity. Okay. And now I'm going to draw a plane that actually intersects with halfway across each axis. So it's actually, here's our plane. Okay, there's our plane. So you can kind of see how this plane is angled. It's angled like at a corner position. How best to describe it? It's like 45 degrees angled, and it's actually perpendicular to this vector. So if you were to draw this vector right here, it's perpendicular to that vector, right? So now we're gonna go ahead and draw. We're gonna go ahead and draw these. Or the Miller indices. We're going to determine the Miller indices for this plane. All right, so let's do this together. So we're going to start with by drawing our steps 1 through 6. And what I'm going to do is I'm going to ask you, for each step that I go through here, I want you to pause the video, and think about how you would do it, right? So you can go back and actually listen to what I posted above if you need to. But step 1, all right, let's think about step 1. What was that again? Well, determine if we needed to move the origin. Move origin. And what was the condition for that? It was so that, if it actually intersects with the origin, we can actually move the position of the unit cell to get more of the plane in the frame so that we can actually define it. So in that case, no, we don't need to, because this plane is still pretty much in the frame. So that answer is no. I'm just going to put an X here to say no. Next, we're going to look at the intercepts. Okay. All right, so let's think about this. What is the intercept? And again, we're just using the same the same Cartesian coordinate grid. I just didn't draw it. So the x-axis here, where are we at? I said it's at the halfway point, right? So just think about, go ahead and do x, y, and z. And it will end up being a over 2, b over 2, and c over 2. There we go. Now we take the reciprocals. Step 4, normalize. And how do we do that again? for planes, we multiply by the distance, a, b, or c. So we're going to get 2a over a, 2b over b, 2c over c. And now we reduce. So before we move on to the next step, what we can actually do is we can cancel. And we get 2, 2, 2. Now we do our reduction. And actually, since we have 2, 2, 2, we can divide the whole thing by 1, or divide the whole thing by 2. We get 1, 1, 1. And then we can close in our parentheses. That gives us 1, 1, 1. And that's our Miller notation. Okay. So common crystallographic planes. I just showed you 1, 1, 1. It ends up being, it's actually the same as, like, okay, so if you look at 1, 1, 1 here, you can see that these are actually intersecting at z, the full extent of z, x, and y. But that's because technically these are the same plane. They're oriented in the same direction. If these planes are oriented in the same direction, they can be anywhere in the unit cell. So really, it's a directionality indication when we're talking about Miller indices. But those are the planes. So you can see the 0, 0, 1 plane is referenced here. These are other equivalent 0, 0, 1 planes. 1, 1, 0 is typically referenced, and then 1, 1, 1. You can also draw Miller indices for hexagonal close-packed unit cells. It's a similar procedure, but it's a little bit more complicated. What you do is you determine the intercepts with the A1, A2, and Z axes. So for a HCP system, we actually have 4 axes: A1, A2, A3, and Z. But for these planes, what you do is you just find the intercepts with A1 and A2 for this one. And then you determine what's called Miller-Bravais indices, H, K, I, and L. Then you follow the same set of steps. So you take your, you ask yourself if you need to relocate the origin. In this case, it's not needed. Your origin's right down here. Then you get your intercepts based on, the position in the cell. In this case, it will never intersect with A2, so you just write infinity A for the A2 set. You take your reciprocals, you normalize in the same method. You get 1, 0, 1 out of that. You reduce to your smallest integer values. And then you determine the index. So that's why that's the little thing that's a little bit different. And in this case, I is negative h plus k. So the height, that's the height of the HCP system plus k. And also you have I is equal to negative. So basically, if we were to write this out, it's equal to negative 1 plus 0. So you get negative 1. That negative 1 comes in right between k and l. Right here. And that's, I'm sorry, that's not the height of the unit cell. That's just this first value. It's HKL and HKI and L. So I goes right here in the middle. See that? There we go. All right, next we're going to talk about planar density. So planar density, or PD, is going to be equal to the number of atoms in a plane, or centered in a plane. Maybe I should add centered here. Centered in a plane. Divided by, that just means that the center point of the atom is somewhere on the plane, or is aligned with the plane, over the area of the plane. Now, I've told you that these planes, they extend beyond the unit cells, so technically they have infinite area, but for the purposes of calculating planar density, we only look at the area inside the unit cell. So that planar density is the number of atoms centered in a plane divided by the area of the plane. All right, so let's just look at a single crystal structure. Or let's actually make it a body-centered cubic. So if I draw our box, we're just going to look at one plane. So we're going to look at the 1, 0, 0 plane. And we'll make it iron. 1, 0, 0 of BCC iron. Okay. And what this will look like is you have a for body-centered cubic, you definitely have an atom in the middle, but because we're on the 1, 0, 0 plane, we're on that maybe the top edge here. We're not going to care about that one in the middle because it's not centered in our plane. So we're actually only going to have these 4 atoms. Okay. Oh. Then this distance here, again, will be A. So in this case, A is going to be equal to 4 over root 3 times R, where the R of iron is going to be equal to 0.124 nanometer. And, you know, I have all these because I have them in my board notes, the radius of iron, for example. They are in your book as well. There are tables that show you where those are. In fact, what I'll do is I might edit this video to actually show you where to find those if you need them. But the radius of iron is 0.124 nanometer. And A, in this case, if you just solve this function, it'll be equal to 0.287 nanometer. So that's just A. That's just the value of this function here. That's one of our side links for the unit cell. Okay. And then that means our planar density, PD, it will be equal to, so how many atoms do you think we have in here? Remember, we have about 1/4 of an atom in this section. So 4/4 would be 1 atom. So we have 1 atom. 1 atom divided by, oh, you can't see. There we go. 1 atom divided by the area of our plane, which would just be A squared. And that'll be equal to 12.1 atom per nanometer squared. And that's our planar density. And this, what we're seeing right here is actually a, we're looking at an FCC unit cell at kind of an odd angle. And we're actually seeing, like, all of the atoms that are in that plane if you were to extend a plane for our iron cell. So this is kind of the same, well, this is FCC, so it's actually it's a different cell, I'm sorry. It's a different cell and a different plane. It's 111, so it's actually that diagonal plane. But what you see along the diagonal for FCC is that you get this really consistent, almost hexagonal looking set of atoms, okay? And so that kind of brings us into something called stacking sequence. So you can actually think of certain crystal structures, especially FCC and hexagonal close packed, in terms of a stacking sequence of atoms. I think I discussed this a little bit in our last lesson. But the very back stack, you could say, is these green circles. And then, or these green, circles. And then the middle stack is the B circles, and then the front stack is the C circles. And if you were to look at this in terms of your HCP structure, this is what you would get like from a three-dimensional view. But you can see that the sequence can be important, right? A sites versus B sites versus C sites. And then for HCP structures, you kind of have a similar thing, except again, it's oriented in a different direction. The order of stacking, or the planes of stacking. So you can see how, if you know along a certain crystallographic plane, you're going to have more atoms than in other crystallographic planes. You can see how that can affect planar density. So you're going to have, let's say, higher density if you're just looking at the, I think this would be the 1000 plane, versus if you had like kind of a plane that looks in the diagonal, right? Because remember, in order to be counted in terms of your crystal structure, or I'm sorry, in terms of your planar density, your plane has to intersect with the center of an atom, the very center, okay? Otherwise, if it does not interact with the very center of a plane, it does not count towards the planar density. Okay, so now we're going to be getting into a small discussion of crystals. So single crystals first. So single crystals on the macro scale occur when, or even on the micro scale, occur when the periodic arrangement of your atoms extends without interruption throughout the entire specimen. So this quartz single crystal is all one giant crystal. That means I can move those unit cells anywhere I want, or let's just say I have one unit cell that I'm looking at. I can move that unit cell anywhere I want through the whole single crystal, and I will still have the same arrangement of atoms, right? Same thing goes for these microscopic images of these diamonds, okay? These are diamond crystals used to actually, as an abrasive, like probably polish material, because diamond polishing is actually quite a big deal. And so this is what it looks like on that micro scale. And then you can also have things as large as turbine blades. This would be a very small turbine blade, but sometimes you do want to make your material properties in a certain way for your turbine blades or other materials. And so there's an interest in actually growing. You have to grow it very slowly, an entire part out of a single crystal of material. That's very difficult to do and is very expensive to do. But this entire turbine blade, this is probably about 1.5 inches. This distance here is probably about 1.5 inches. It's a very small one. All one single crystal, which is pretty impressive. Which, there's a big hint up there on why we're even talking about this to begin with. It's because, whether or not it's single crystalline or polycrystalline, and the arrangement of those crystals, it will have an effect on your material properties. And then we're going to differentiate from single crystals by talking about polycrystalline materials, especially steels. I don't know what this is. This is a, I don't remember what NB is, but I think it's hafnium plate. So NB and hafnium plate with an electron beam weld. Okay. So this is a material that has been welded. I guess these two materials have been welded together, and this is the weldment. And what you see here is actually this has been etched so that you can actually see the difference in the crystals that are within this solid material. And of course, they stick together still. There's the grain boundary where different crystals, meet together and they actually connect through atomic bonds, actually. But they're not perfect, and so there are definite regions of difference between them. And so that's what this looks like. So we have very fine or small grains on this side, and then we have really large grains on that side. So each grain is a single crystal, and the grain sizes typically range from about 1 nanometer to 2 centimeters. So from a few to millions of atomic layers. Okay, so now we also have anisotropy versus isotropy. Anisotropic materials are basically materials that they have different material properties in different directions, or different geometry even in different directions. Isotropy means that they're the same in all directions. Okay. So single crystals, they can be highly anisotropic, actually. So they tend to want to be stronger in different directions. So if we look at our Young's modulus, again, I don't think we've talked about Young's modulus and what that is. It's a stiffness value. It's extremely important to mechanical engineers. Young's modulus will be something you have tattooed to your brain. But all you need to know is that for this body-centered cubic structure, the Young's modulus is much stiffer along our 1-1-1 direction than it is in I think this is the 0-1-0 direction, or even any of the others, just because that has a higher a higher linear density in this direction. There are more atoms to contend with in this direction than in that direction. So that's why it's 273 gigapascals in this direction versus the other. However, polycrystals or polycrystalline materials, they can change in direction, but because we're like jumbling them up, it's kind of like take a bunch of these crystals, these unit cells, and just throw them into a box with different orientations. It will end up actually averaging out your different material properties. So what it'll do is it'll make it more isotropic. So if the grains are randomly oriented, the properties are isotropic, which is very helpful. It can be very helpful. If the grains are textured, so if they have like a deformed kind of style, like if your grains tend to be shaped in certain ways that are directional, then they can be anisotropic. Okay, so why would engineers prefer? So, for example, I showed you this turbine blade. Why would they prefer this anisotropic structure over an isotropic structure? Well, maybe they want to maximize the resistance to, let's say, gas pressure in just one direction, right? Whereas I would say most of the time engineers prefer to work with isotropic materials like aluminum, usually like standardized aluminum and steel. They tend to be isotropic materials. And we prefer isotropic materials because we don't have to run constant tests on our material to figure out which way we're looking. I don't know if that makes sense. You can't tell easily which way your crystal structure is directed. You have to use like a scanning electron microscope or something, and it's a lot of work. Engineers tend to prefer this kind of jumbled set of polycrystalline cells or grains, because we can just order a piece of steel, get it and cut it out any way we need to, and we're sure it'll still behave in the same way in one direction versus the other, even if we are sacrificing a little bit of our ability to make this as efficient as possible, right? Like maybe our Young's modulus is lower overall in every direction, but it's cheaper, like way cheaper to make this stuff than growing it all from a single crystal, and also because it's just convenient. Okay. And now we're going to talk about isotropy and anisotropy. So I think I've kind of already covered it, but I'm going to draw out the definitions because that's what I like to do. So anisotropy first just means that the material properties are different based on direction. Okay. And then we have isotropy. And you can guess what that is. It's just the opposite of what we have above. Material properties are the same in all directions. That's important. And then again, I kind of already talked about this, but which do engineers prefer? Oh, I mean, you can't see that. Which do engineers? Oh, man. That is terrible, terrible writing on my part. Apologies. But which do engineers prefer? And, you know, I already kind of mentioned it, but mostly isotropic materials. That's usually what we prefer, but there are specific use cases like that turbine blade, and, you know, some other things you could probably think about it, like really, really high performance vehicles, for example, like F1 racers, that kind of thing, that you might want to use really expensive single crystal materials or anisotropic materials to make work. In fact, most composites are actually anisotropic. So carbon fiber, for example, is highly anisotropic. So usually you can make carbon fiber isotropic, but that's a long discussion. But anyway, so it's situational. The answer is it's situational. Okay. All right. We're going to take a look at slide. Okay, so I already discussed anisotropy and isotropy. So now we're going to come down and we're going to discuss polymorphism. Also known as allotropy. Okay. So polymorphism or allotropy, these are synonyms. This occurs when there are two or more distinct crystal structures for the same material. Now, I'm not talking about direction. I'm not talking about grains. I'm talking about crystal structures. So, like, I mean, like FCC versus HCP, or or single crystal. I mean, we don't really encounter single crystal often. BCC versus FCC, right? Crystal structures for the same material. And there's one really, really great example of this that we will talk about a lot in this class, and that is the iron system. The iron system. It is very important to human society. It is very interesting to me that God gave us this in the iron system. It really meant, like, you can look at different properties or mechanics in nature. We should say mechanics. I mean, this is mechanical engineering. There are different mechanics in nature that God has given to us to use to our advantage. And some of them are just very interesting, like electricity, for example. God gave us electricity, and because of that mechanic in our environment, we can, create digital content now and talk to each other over the phone or through FaceTime. And it's just interesting that God gave us access to this, right? Well, the iron system is, I would say, equally interesting. And people who aren't engineers really don't understand iron and steel. Like, they just think it's a hard metal and, that's great and everything. What they don't realize is that it's actually really, really complex. And because of the complexity, it's extremely advantageous to human society because we can leverage that complexity in a bunch of different ways. So what we find in the iron system is that if you start at a liquid molten metal of molten steel at 1538 degrees Celsius and you cool it, or it'll start with at delta Fe or delta iron in a BCC crystal structure, and if you cool it below 1394 degrees C, it will change to a gamma iron or FCC crystal structure, and then you cool it. If you continue to cool it, it'll change down to below 912 degrees Celsius, it'll change down to alpha iron, which is also a BCC crystal structure. Now, this adds to some of the complexity that we'll talk about related to steel in particular, but that's just something to keep in mind as we go forward. So this is what's called an allotrope. So these delta, gamma, and alpha, these are different allotropes, and we differentiate between alpha and delta by the temperature. So that's it for now. And the next lesson will be uploaded later today or tomorrow. We're going to have 4 lessons this week, and my goal is to have all of those uploaded by the end of the day, tomorrow, or at the latest by midday Wednesday.